Hi everyone, my name is Supporter Isaac Berry from Berry Science Lab, and today we're going to be discussing, pretty shortly, a very important topic in analysis, measure theory. So, what is measure? Well, in the physical world, a measure is any property of a specific object that can be quantified. So, for example, we could point to this object and talk about its temperature, or maybe its weight, or maybe we could talk about its length, or surface area, or volume, or maybe we could talk about, its density, or we could talk about its stress strain coefficient. There are a few things we could talk about for any given object, or you could talk about even its color, its hue. You could talk about its opacity. You can go on and on and on, right? So, all of these are not properties of just this one object. All of these are properties that you can quantify for any other given object. We can also assign a mass and a temperature and a volume, and well, technically not really these two. Well, we can still assign surface area and length. We can assign to its radius. We can assign density. We can assign hue. We can assign opacity. We can assign all of the measures that we assign to this cube or cuboid onto this sphere. So, mathematically, measure takes a little bit of inspiration from what we mean in the physical world. So, given some set, a measure, M, which takes in a set and returns some, well, not strictly positive, it could also be 0, some non-negative real number. So, one of the most important measures in this regard is the Lebesgue measure. I have no idea if I pronounce Lebesgue or Lebesgue or whatever it is correctly, but I'll just say Lebesgue measure, right? Because this allows us to generalize our concepts of length, area, and volume in 1, 2, and 3 dimensions, respectively, to any dimension. So, we could talk about the volume, or hypervolume, of a hypercube. Trying to depict a 4D object on a 2D surface, and I don't think it's going to go well. Something like that, right? So we could talk about the volume of this hypercube right here. So that's what the Lebesgue measure allows us to do. It also allows us to talk about the length of normally weird-looking entities like, the Cantor set, which is just composed of points. Spoiler alert, it actually has 0 length. Or we can talk about space-filling curves, and the like. So, this is one of the most important measures. But let's first talk about measure in general. What are the axioms of measures? So, what properties does it have to satisfy? Well, first of all, the measure of the empty set is always defined to be 0. That's it, 0 in the real numbers. The measure of any two sets added together, technically we can't use this, we have to use union notation. If these two are disjoint, is equal to the sum of their measures. And we can actually generalize this property. We can say the measure of the union of infinitely many sets that are all disjoint from each other, and yes, the empty set is disjoint from itself, is equal to the sum of the measures of the individual elements, right? So, these are the two big properties of measures. So these are the rules that we're generally operating on. The measure of the empty set is equal to 0, and the sum of the measures of disjoint sets is equal to, well, the measure of the union of disjoint sets is equal to the sum of the measures of each of the sets. Right. So, one side effect of the second property is that something like, for example, I don't know, if A is a subset of B, that implies that the measure of A is less than or equal to the measure of B. Why? Because we can define some new set C, which is just B without A, or in other words, B with all of the elements of A taken out. Well, you know what? Right. So this is a new set of its own, and we can also safely say that this is a subset of B, right? And then we can also safely say that C is disjoint with A because all of the elements within it are also part of A complement. So we can be confident that the measure of B, which is equal to the measure of A union C, by this axiom, since these two are totally disjoint, is equal to the measure of A plus the measure of C, which this has to be greater than or equal to 0. Hence this. Okay, so now let's talk about the Lebesgue measure. So we're going to get to it in only one dimension today, R, which means that the Lebesgue measure is going to be equivalent. So we're now formally defining length, right? So we're going to say that the length of any set, not just intervals, any set, S, which is a subset of the real numbers, is equal to the infimum of the Lebesgue measure. Well, it's technically not the Lebesgue measure. Did it freeze? Wow. So it's the infimum of the union of, okay, so it's the infimum of the length of the union of some cover of the set, IN. So, actually, I can rewrite it this way. Okay, the sum from n equals 1 to infinity of the length of IN, provided S is a subset of the union of all sets IN. Okay, so we can find some sequence I, we can make it up, and the sequence we can make up such that this is the smallest, we're going to go with that value, right? So that's a pretty unclear explanation. So let's start by trying to find the very much expected length of an interval, or Lebesgue measure. Of an interval. We expect the Lebesgue measure from A to B to be equal to B minus A. But what is it really? Well, let's find out. So first, we can come up with some sequence I such that I1 is equal to the interval, I don't know, A minus epsilon, B plus epsilon. And this has to cover the entirety of AB for any epsilon greater than 0. So I'm just going to set I2, I3, etc. equal to the empty set, right? So then, the measure, Lebesgue measure of A comma B, since it's a subset, since this has to be a subset of that union, remember what we covered before about subsets, which implies that this measure has to be less than the Lebesgue measure of, well, the union of all sets is the exact same as just I1 by itself, since I2, I3, etc. are all empty. Did I draw the line and the empty sign the right? Whatever. Okay, so this is equal to what? Oh, crud. By definition, it's supposed to be. Not sure how I made that mistake. Okay, great. So the length is just the upper limit minus the lower limit, right? So we're fairly sure that the Lebesgue measure of A to B has to be less than or equal to B minus A plus 2 epsilon. But we can make epsilon arbitrarily small, and this will still hold, implying that the infimum of this will mean that this has to be less than or equal to B minus A, right? Okay, so we've established a lower bound